Okay. Yes, so she asked for number 4 on this take-home quiz. Maybe I won't do the whole thing, or maybe I won't do one exactly like it, but I'll do one darn close to it. Look at this. I'll just make one up. Okay, so this is a function. It's the cube root of 7x plus 18 squared. Cool. What's yours? On your number 4, it's 15x minus 210 squared. It's a cube root squared. Anyway, if it's a cube root squared, you know, the better way to write it might be like this. 7x plus 18 to the 2/3. That's a cube root squared. And then what my directions say is do a first derivative test, a concavity test, do it, do everything, and I could do everything and see what this graph is doing, increasing, decreasing, concavity. I should do all that work, I guess. The other thing you can do is you can pick up a graphing calculator and type it into your graphing calculator. Again, I don't do a lot of that with you. I used to bring a calculator in here and shine it on the board, and then my thing broke. The computer has a calculator, but it's a little cumbersome to turn that on all the time. So I've gotten to where I don't really show you me working on the calculator, but I always assume you can be working on the calculator. If you type this in and take a look at it, I don't know. I kind of know, but I could be wrong. You get something like this, or actually maybe something like this, or maybe it's upside down.
It's upside down.
Okay. So it's something like, but maybe you don't even know how to. I don't know. I'm worried sometimes maybe you don't even know how to use your graphing calculators. Maybe you don't know how to get here, but you just got to go to y. You go to y equals and you type in the equation, and then you play with a window. Usually the key is messing around with a window so you can see this thing. But I've mentioned that before. Again, I've never brought in a calculator and gave you calculator lessons. So anyway, I hope you know how to do it. I think I got the graph, but if I want to do all the work and show all the work, because I do grade the work, that you'll see that when I give you back some of your stuff. I always grade your work. Anyway, let's do a derivative. Derivative's kind of easy. 2/3. It's just a power rule, right? 2/3 to the negative 1/3 times the derivative inside. 7. So that was easy. I could do a second derivative real quick, although I want to stop and analyze this. But let's just, while we're doing this, let's do a second derivative real quick. Second derivative is kind of easy. The 1/3 comes down. Well, I don't know how you guys want to think. Let's see. Maybe what you'd like me to do is call this 14/3, right? That's what this is.
Right.
7x plus 18 to the negative 1/3. Okay, so I did a slight bit of cleaning there. Now I'll do a second derivative. Negative 14/9. And then you subtract 1, right, you guys? Chain rule says spit out a 7. It's a fairly easy derivative to do. And then what you find out, though, when you stare at this first derivative, what it is it's a 14 over 3. And then this thing is in the denominator. It's a cube root in the denominator. And then the question is, looking for critical numbers, when does this equal 0?
No.
Never. And I don't know if some of you got that. I graded your last quiz last night, so I noticed some errors. This thing equals 0 when the numerator equals 0. The numerator equals 0, never. So this never equals 0. There's probably no horizontal tangent lines. If it never equals 0, there's no horizontal tangent lines. The derivative never equals 0. When is the derivative undefined? When the denominator is 0. When does that happen? when x is negative 18/7. Do you see that? When you set this little thing equal to 0 and move the 18 over and divide by 7. I mean, when does this equal 0? When does the denominator equal 0? You can ignore the cube root. You can ignore the 3. When does this denominator equal 0? Negative 18/7. So that's a critical number. It's a critical number that made my derivative undefined. So it's a critical number. Well, wait a minute. It's only a critical number if it's defined in the original function. Is it defined in the original function?
Yes.
Yes. If I plug in that negative 18/7, I get a 0. That's this point right here. Negative 18/7 is 0. In the original function, it's defined. It's a 0. In the first derivative, it was undefined.
So it's critical.
So it's a critical number.
If it wasn't.
But by the way, you know, there's two kinds of critical numbers, right? I mean, there's the kind that make the derivative 0, and there's the kind that make the derivative undefined. I mean, I don't know. Both of those are critical numbers. That's the definition of a critical number. It says it makes the derivative 0 or makes the derivative undefined. But visually, you know the difference? When it makes the derivative 0, those are slopes of 0, horizontal tangent lines. When it makes the derivative undefined, those are sharp points, end points, vertical tangents, right? When the derivative is undefined, it's a little weird. But it could still be a critical number. I mean, it is. So anyway, I'm just saying, I got a critical number. It ain't one of them kind. It's some other kind. By the way, you already see it. It's a sharp point, is what it is. Anyway, what do? I guess I should put that on a number line, you know, negative 18/7 and test around it. You know, so over there to the right, I think I'll pick a 0. And I'll plug it into what? The derivative, right? I'm trying to see if the derivative's positive or negative. You know the game. If I plug a 0 into this derivative, it's positive. It's the cube root of 18. I don't care what it is, but it's positive. This is positive. This is positive. It's positive over there to the right. It's increasing. What about over on this side? Maybe I better pick like a -3 or a -4. If I pick a -4, this is a negative number. The cube root of a negative number is negative. This thing is negative. So it's decreasing. So I just discovered he's a min. And if I plot him like I do in the original function, I find out his y value is 0. So I already kind of got him plotted. And I already got the graph drawn. You know, I cheated. No, I didn't. Sorry, that's the wrong word. I picked up my graphic calculator and looked at my graphic calculator. That's what it looks like. But I can tell, so I'm cool. You know, I'm sort of checking my work. That's decreasing and then increasing. That's awesome. The concavity is a little strange on this one. Let's see. Let's look at this second derivative. I'm looking for inflection points. By the way, just look at the damn picture a second. Do you see any inflection points?
2.
Good. It's kind of strange. I mean, there's a sharp point there. There's an important, funny, sharp point there. By the way, it came out as a min, is what it did. Does it look like a min? It looks like a min. But what's the concavity doing around it, according to my picture? According to my picture, it's concave down, and then after that, it's still concave down. And so if it doesn't change concavity, it ain't officially an inflection point. So I would say it's not an inflection point. Of course, I haven't done my thorough analysis. I've just done my visual analysis there. My thorough analysis would require me to look for possible inflection points. I would look for possible inflection points by thinking about, when is this 0? Again, can you, without me writing this, can you imagine this is in the denominator, right? So when is it 0? Never. When is it undefined? When this same place, this negative 18/7, don't you think? So that's a possible inflection point. He made this second derivative undefined. He's possibly an inflection point. We already know he's not. If I put him on a number line and test around him, I got my negative 18/7. I'm checking my second derivative number line. I'm checking what's called the concavity test. I should find out it's concave down and concave down, right? That's what I should find out. I'll just pick something like 0. I'll plug it into the second derivative. It's kind of a mess. Maybe you'd like it here. Let's clean it up just a tad. What is 14 times 7? 98. Negative 98 over 9. And this dude's in the denominator. It's a 7x plus 18 to the 4/3. So what am I going to do? I'm testing a 0. Thank you. I plug in a 0. I get 18. Raised to the 4th, cube rooted. I don't care. It's positive. Times 9, it's positive. But the numerator is negative, so it's negative. So this is negative or concave down. We already knew that. Over here, I would test like a -3 or -4. I'll try -4 again. That's negative 28. That's a negative number in there. And when you cube root it, it's negative. But when you raise it to the 4th, it's positive. But the numerator is negative. So it's negative. And it's concave down. So, I'm decreasing, watch this, I'm decreasing concave down, and then I start increasing concave down. That, when you do that, you form this sharp point, that like we saw in this picture. So that was a good problem. She asked for a problem like number 4, and that's a hell of a lot like number 4. Just put some different numbers. But it was fun. It was a thorough analysis of this function. What else? Any other good questions? Okay, number 5. Yeah. All right. I think I might, you know.
Yeah, he's done that one before.
Well, I'll tell you what I'll do with number 5. I'll just kind of get you started. I'm not going to finish this one. And I'm not going to do one similar. I'll do number 5, partially getting it started. I mean, that picture helps a hell of a lot. There's a picture there of a pen, and it's got a bunch of cross fences, 1, 2, 3 cross fences. You know, I said 3 cross fences, but then there's these 2 end fences too. And what I would do is I would label these X. And by the way, once you label one of them X, they're all X, because it's a rectangle. They're all the same width. I'm labeling those widths X. And then I'll label these lengths Y, I guess. And then I know something about the perimeter, I think. I mean, all this fence has to add up. How much fence do I have? What did it say?
800 feet.
300 feet?
No, 800.
Oh, 800 feet. So all this fence has to add up to 800. So what is all that fence? 1, 2, 3, 4, 5 X's and 2 Y's. This is easy. This is easy. What?
And then you just saw for 800.
Well, maybe. I mean, there's more to it. No. I mean, no. So that's one true fact, that I got 800 feet of fence, and I got to build all these damn fences, and this is a true fact, that 5x plus 2 y's have to be 800. But the other thing I'm trying to do is maximize the area of this thing, and just try to picture the whole thing. Forget all the cross fences. The whole thing, the area of the whole thing, please. X times y, width times length, x times y. And this is the guy you're trying to maximize. So you want to do his derivative. You know, when is he a maximum? Well, you'll take his derivative, you'll set it equal to 0, you'll find a critical number, and that's probably it. You'll take his derivative, you'll set it equal to 0, you'll find a critical number, and that's probably it. That's what makes it a maximum. Listen, this ain't hard. If you want to find out when something's a maximum, you take the derivative, you set it equal to 0, and you find that critical number. Okay, now what's the little problem here? I can't do a derivative of an x times y. I need one variable.
Solve for x or y on that.
Okay, that's what this equation is supposed to help me do. Right, so before I do this derivative, I need to get it all in, I need to be a function of x, or get it all in one variable. So if you did solve for y here, it would be 800 minus 5x divided by 2. You could write that a couple ways. You could call it 400 minus 2.5x. Anyway, plug that in for y, and then you'll have a nice area function. You'll take its derivative, you'll set it equal to 0. I'm going to shut up and let you finish this one. Right? It's easy. You'll find it. You'll find one critical number. That's going to be the answer. Wait a minute. What's it the answer? It's x. It's the width that maximizes the area. What's the question one?
The largest possible.
Oh, it wants the area. So sometimes they ask for the dimensions or the width. So when you find the critical number x, that'll be your width. If you take that x and plug it in here, you'll have y. That'll be your length. If you take your width times your length, you'll have the area. So I think you can answer the question, but the key is finding that critical number x when the derivative equals 0.
Yeah.
I mean, that's this whole chapter, dude. Take the derivative and set it equal to 0.
Yeah.
But sometimes it's in a word problem, sometimes it's, right. And I keep saying take the derivative, set it equal to 0. Sometimes you got to watch out for when it's undefined. That's what this one was. This derivative never equaled 0. We had to look for when it was undefined also. I mean, there's little details. Anyway, that was fun. Number 5, got you started on 5. What else? Any other good ones?
I have a question on the homework.
Okay, what is it?
In 4-7, number 13, minimum distance.
Yeah. All right. So that's an applied max-min problem, like this one, except probably a little tougher. Number 13 is about minimum distance. That's a good question. Let's do it. In the homework, I've seen this show up on a test, maybe. Have we done any like this? Okay, well, it's about damn time to do it then. Thank you for asking. 4.7, number 13, says, find the point on the graph of this function that's closest to the given point. All right, so I've got a function. The function is called f of x equals x squared. They also give me a point. And here's what they're saying. I'm going to draw a picture of this. They gave me this function, which we all know is this parabola. And then they gave me this point, 2, 1/2. So their question is, find the point on the parabola that's closest to this point. So watch this. There's probably some point on the parabola. By the way, it's probably somewhere right there. There's some point on the parabola, but I don't know what it is, right? So I'm going to call that point x, y. And then I want this distance to be, the minimum distance. I didn't want to say that. I wanted to make you say that. The question wanted the closest point. Can you translate closest point into a different words? Closest point? How about minimum distance? Anyway, right. So that means I want to minimize the distance. All right, well, maybe I better make up a distance formula problem. All right. Do you know how to create a distance between 2 points?
The square root of x.
It's just, it is the square root of, and then you subtract your x coordinates, x minus 2 squared, plus subtract your y coordinates, y minus 1/2 squared. Yeah, that's kind of nasty, but that's the distance formula between 2 points. Perhaps we should know the distance formula between 2 points. It's not too bad, but it's kind of out of left field sometimes. So now I want to minimize this. I want to take its derivative, set it equal to 0, blah, blah. I want to minimize this distance. I want to, find its critical number. I want to minimize this distance. Well, listen, I can't take its derivative yet. There's too damn many variables. Is there any way to get rid of this y? Is there any way to get rid of this y? If this point lives on this function, like it does, then what's y?
X squared.
X squared. Okay, y is x squared. So I can change y to an x squared. If your point lives on this function, your y value is x squared. Okay, so now I'm going to change it to this. Hey, I'm also going to ignore the square root. I'm totally dropping the square root. You're allowed to do that when you have a master's degree. good. You guys okay? Anything bothering you? When I read this problem, I decided I needed a minimum distance. So it was up to me to grab a distance formula out of my head. I did. And what I had was an unknown point that I'm trying to find. What's the point that's closest to this point? So I did a distance formula from an unknown point to a real point there. I had too many variables, so I got rid of y, because I know that if you live on this function, that's your condition, you know. That's the same thing as like the farmer had 800 feet of fence. This was your condition you were allowed to use to help you get rid of the variable. Well, the condition I'm using here is that this point lives on this function. So I'm allowed to substitute y for x squared. And now I want to take a derivative and set it equal to 0. And then the thing I kind of quickly glossed over is I dropped the square root. So, you trust me on that? Or should I explain it? You trust me, huh?
Yeah. It's gonna be square both sides.
You should be more,
Zero.
you should be more inquisitive. You don't just trust Trump when he tells you all that shit, do you? So don't trust me either. Listen, now here's the concept. The concept is, what's the concept? Oh, we're trying to find a minimum distance. Listen, if I've got this distance, this distance, this distance, this distance, if I've got all these different distances, one of them's a minimum. If I squared them all, they would all change, but the minimum one would still be the minimum one.
Yeah.
So the point is, in these distance problems, and it happens 2 or 3 times in calculus, when you're trying to minimize a distance, what you can do is you can do the distance squared instead. You can ignore the square root and do the distance squared. The problem is I called this d. This really is d with the square root on it. When I took the square root off of it, it's not really d anymore. You know, I mean it's not. It's d squared, and I don't really want to call it d squared because I don't want to complicate things. Can I just call it d? All right, here I go. It just simplifies the derivative. Here I go. I can minimize this. So I'm taking the derivative of this without the square root. You bring the 2 down. X minus 2 plus, that's it, right? Is that it? Well, the derivative inside. The derivative inside is 1. Yeah, okay, thank you. And then the derivative here would be 2. X squared minus a half. And then the derivative inside? 2x. Okay, look at this, you guys. It's kind of complicated, but this is my derivative, and it's a maximum or a minimum when I set it equal to 0 and find the critical number. So I'll set this equal to 0. Let's see here, 2x minus 4, if I distribute, I'll distribute this. Uh-oh, that's a 4x cubed. I'm distributing all this, you guys. That's a 4x times this, and that's a minus 2x. Distributed all that. I'm going to collect like terms. Oh, those 2x's fall away. Whew, that was nice. So I got a negative 4 plus 4x cubed equal to 0. Yeah, this is going to be easy, right? Move the 4 over. 4 equals 4x cubed. Divide by 4. 1 equals x cubed. Take the cube root of both sides. X equals 1. That's your critical number. That's the point where we have a minimum distance. By the way, the picture kind of looked like that. When I drew the picture, kind of looks like that could be the point 1, 1. Turns out it is. That's the answer. The point 1, 1. Well, I know x is 1. How do I find y? Oh yeah, here's y right here. So if x is 1, y is 1. So the point is 1, 1. What was the question?
What's the minimum distance between?
Oh.
Actually, the question was, find the point on the graph that is the closest. So the question wasn't, what's the distance? The question was, find the point that is the closest. So we got it. We got it. The point is the point 1, 1. Are you guys okay? This was a good problem. I mean, we hadn't done one like this yet. It was in the homework. I assigned it. It's a minimum distance problem. The funny little thing I did was, rather than do the square root, I just took the square root off and minimized this distance squared. But it still produced a minimum. And it simplified my calculations a little bit, right? The derivative would have been a little more of a pain with that damn square root on there. Yeah?
What if you wanted to find the distance, do you just plug it into the original?
That's true. If they wanted that distance, now that I got the x and the y, I can plug the x and the y into the original that does still have the square root because that is the distance. And I can plug that 1 and that 1 in there and calculate the distance. Right. The minimum distance occurs at that critical number, which generates this y value, which then I've plugged in here you can calculate that minimum distance. Yeah. What else? Yes, sir.
Can you number 8 from the take-home quiz?
Number 8 from the take-home quiz? Yeah, maybe. I could do that one. I like those. So there's an 8 and a 9 there that are sort of similar. Maybe I don't mind doing 8. Listen, without writing it all down, maybe I'll just do number 8 here. It says sketch a graph given these facts. Well, let's see what these facts are. It says f of 2 equals 3. Well, f of 2 equals 3. That's like a point on the graph. I guess I could f of 2 equals 3. F prime of 2 is 0. So at this point, the derivative is 0. So that makes me think it might be a min or a max. I don't know yet, but it's the derivative is 0 at 2. It's what it said. It says f prime of 2. See, I think sometimes you don't know how to read these things. F prime of 2 equals 0. So 2 is a critical number. It made my, maybe I'll put it on a number line, you know. 2 is a critical number. Oh, shit. F double prime of 2 is 0. F double prime of 2. So it's also maybe an inflection point. It makes the second derivative 0. So maybe I should put it on my second derivative number line. Call that y, whatever. Are you guys with me? 2 made the derivative 0, so I'm putting it on a number line like a critical number. 2 made the second derivative 0, so I'm putting it on a number line like a possible inflection point. And now I'd like to test around it, but I don't have a function to test, but they tell me, they give me the information. They tell me right now, the next 2 lines say that when x is less than 2, the first derivative is less than 0. Can you read that? It said f prime of x is less than 0 when x is less than 2. That's what it said. So it says when x is less than 2, the derivative is negative. So the derivative is negative. The first derivative is negative. So it's decreasing. That's what they just said. And then the next line, I think, says when x is greater than 2.
No. Oh, yeah.
When x is greater than 2, the derivative is still negative. That's interesting. It says, and again, I didn't want to write all this down, but this is what it says. It says when x is greater than 2, the derivative is still negative. Huh. So it's still decreasing. So, all right, well, then it ain't a max or a min.
Right.
It was, if you remember, though, it was a little level spot because it said it had a slope of 0, it said. Yeah. So it's kind of a little level spot, but it's decreasing and then continues to decrease. I mean, I can almost draw it without looking at the concavity, right? How do you decrease to a level spot and then continue to decrease, you know? You decrease to a level spot and then continue to I mean, that's the only way to do it. But if I read the concavity, which is the next 2 lines, it'll probably say what I see here. What do I see here? Concave up and then concave down? Yes. Let's see what it says. When x is less than 2, the second derivative is positive. When x is less than 2, it's positive, so that's concave up. When x is greater than 2, the very last line, the second derivative is negative, So that's concave down. So that's what I'd like to do. I'd like to decrease concave up and then continue to decrease concave down. And that really is an inflection point. Okay, decrease concave up and then continue to decrease concave down. Yeah, that's it. That's number 8. Cool. That's what, you just got to read all that information. It's all there. It's kind of like they're giving you a first and second derivative test. You just got to read it. You just got to read it out of here and sort of put it on a number line.
29 from 4.8.
4.8, 29. We could, listen, so listen, she asked this, we did get into 4.8 the other day, and I don't know, I don't know how well that went. So let me just summarize 4.8 again for you real quick. Here's what we learned in 4.8. We learned about these differentials, but let me just try to summarize. Listen, there's this thing called the change in y. We all know that that's a y minus another y, but the way we usually write it is using function notation. I mean, what I usually write is f of x plus delta x, see that's one y value, minus f of x, that's the other y value. Is that okay? I mean, you're staring at me weird, and this is very basic. A change in y is the subtraction of two y's. To get two y's, you kind of need two x's. So you plug this x into the function, you plug this x into the function. So what are the name of my two x's? One of them's an x, and the other one is x plus delta x. So these are two different x's. I plug them into the function, I get two different y's. Subtracting two y's, you get the change in y. Okay, then we learn, so that's one thing, that's one idea. But then we learned about this thing called dy. This is called the differential. And what we said is it's just f prime of x dx. So that's not too weird. I tried to explain it by saying this. Isn't the derivative dy dx, isn't that just f prime of x? I mean, isn't this just two notations for the derivative? And then you can sort of algebraically imagine multiplying the dx over to that side. And then you've got this relationship. It's not a bad explanation. So so this is the relationship between dy and dx. So that's it. And then, so how does this show up in, how might I ask you a question? What we said is these are used sometimes in error word problems about error. And then the little dy is the error in measuring y. dx is the error in measuring x. And then we kind of just use this formula. I mean, this is kind of insignificant up here, actually, for certain problems. We just use this. So for error word problems, those are kind of good. Now, what she asked me? She asked me for 29. That is a nice error word problem. Let's see what it says. It says, the measurements of the side of a square floor tile is 10 inches. With a possible error of 1/12 of an inch. No. 1/32. Thank you. So what did I just read? That they're measuring a square tile, and can I call the side x? And what was the measured value of x? 10, I think it said. Did it say 10?
10.
It said 10. And what was the error in measuring x? 1/32
of an inch.
So I'm going to call that, this is 29. Out of 4.8. So I'm going to call that dx, the 1/32 of an inch. Are you guys okay? I mean, and so the question is, the measurement of the side of a square is 10 inches, but it has a possible error of 1/32 of an inch. Okay, so use differentials That means this kind of idea. Use differentials to approximate, and that's kind of, the idea was that the dy here is a good approximation for the actual change in y. So we're going to use dy to approximate the actual change in y. So we're not really doing the change in y, we're doing this. We're doing this guy. But we're doing it to approximate. Use the differentials to approximate the propagated error in calculating the area of the square. The error in the area. Say that 5 times real fast. Never mind. Okay, I'm going to try that. So can I come up with an area formula for a square? Good job. Can I find the relationship between dA and dx? I mean, I think what they just asked me for when I read that is use differentials to approximate the error in calculating the area. Did they say they want the area?
No.
No, they said they want the error in the area. What do you call error in area? Well, dA. Right. So that's what they asked for. They gave me that, they asked for that. I've got this, I pulled this out of my head. So I think I should do a derivative. But it's this new kind of derivative. It's this, I want to do this derivative where I go like this. The derivative of A is dA. That's how I do it now. And then the derivative of the other side is 2x. And then out on the end I put a dx. I mean, this is, it's not really, I mean, it's a new notational way of doing it. It's not really a new way of doing derivatives, but it's just a subtle notational difference. But now I got this, dude. They want, here, I got this. The x was a 10. That was the measured value of x. The error was the 1/32. And so when I calculate this, this will be the error in the area. The error in the area is 20-30 seconds. 20-30 seconds. That's 5/8 of an inch. Or actually, it's inches squared.
5/8 inches squared.
I mean, this was real easy, but I know it's kind of new. We just explained it the other day. It's this kind of idea, which is a real easy idea, but put into a word problem, what the hell are we doing? We're calling these little things errors. These are errors in our word problem. Part B wanted a percentage error. This is the actual error right here. This is the answer, dA. The error in measuring the area is 5/8 inches squared. The percentage error is dA over A. So what was the dA? 5/8 inches squared. What's the actual measured area? As if there was no error. If x was just 10, what would be the area? 100 square inches. So 100 inches squared. So the actual dA over A, watch what happens. The units cancel, so this becomes a unitless. This is unitless, and it's just a decimal. It's 5/8 over 100. Can you tell me what that is? 0.00625. I mean, that's the... Now, to make it a percent, you would actually multiply by 100 again, which is not this 100. This 100 was my area. But to make it a percent, you'd multiply by 100. You could call this 0.625%. That's pretty small, dude. I mean, right? Less than 1% error. Of course, this error was small, right? Wasn't this small as hell? 1/32, right? So this was a small error. So we wouldn't expect too much error when we calculate the area. But it does, error kind of compounds itself, right? I mean, you've got this one measured error, but when you start doing calculations with this error, the error gets a little worse, maybe. So this is darn good. but it is a little worse maybe than because it was used in this calculation. Whatever. That was fun and easy. So I like, listen, so if I'm putting anything from 4.8 on the test, it might be something like this. It might be an error word problem where your idea is, you know, I don't know, it's this idea, it's this idea, it's the idea of reading the problem and calling this an error, calling this a measured value with an error, looking for an error. Yeah. But the other kind of problem I like in 4.8 is something different. Can I show you something different? Watch this now. Watch this, because I don't want to confuse you. But when I start to tie these together, watch what happens. If this dy is f prime of x dx, right here, that's what this is, and it's approximately equal to delta y, which is this, then I do one move on this. I move this over here, and I create this. F of x plus f prime of x dx equals f of x plus delta x. So, I hope I'm not losing you or confusing you here. Listen, it was pretty easy. It was this idea and this idea, but then I put them equal to each other because dy equals delta y. Now wait a minute, I said equals, but I meant they're approximately equal, and so I set them equal to each other. And then I move this f of x over, and I got this relationship. And then this is useful for questions like this. What's the cube root of 120? And if I'm asking you for this, then this is this side. So, can you identify an x and a delta x that would give me this 120? And oh, can you identify a function? I need a function, I need an x and a delta x that would give me all this. What function would it be? I think it'd be the cube root of x. What do you think x would be? Pick a nice perfect cube root. Maybe you don't know perfect cube roots as good as me. 125 is beautiful, perfect. The cube root of 125 is 5. So I'm going to pick x to be 125. But wait a minute, if x is 125, how do I want it to be 120. So what's my delta x? Negative 5. So now, if this is my function, and you take x plus delta x and stick it in the function, I mean, do you see how this is this? Do you see how this is this? All right, but I ain't using this side. I'm using this side to approximate it. So here I go. Okay, what's this then? This is my function. This is the cube root of, and what am I plugging in here? 125, yeah. So this is going to be a damn 5 right here, right? What is this? Oh, this is my derivative of my function.
Yeah.
Okay, what's my function? This is my function. All right, what's my derivative? 1/3 x to the, yeah, 1/3 x to the negative 2/3. Or 1/3 x to the 2/3. Great. Okay, that's my derivative. 1/3 x to the 2/3. What am I plugging in for x? What am I plugging in for x?
Negative.
What's x?
120.
125 to the 2/3. And what is, I got to multiply by delta x, or dx. dx is delta x, sorry. dx is delta x. So I multiply by a negative 5. This is my, I'm using this to approximate the cube root of 120. I thought I just explained it better, but maybe I didn't. I tried to. You got to identify a function and an x and a delta x. The delta x is dx. And that's the key. And then this formula kind of works. And maybe it's a new memorized formula, but it's not really a new formula. It's this idea. When you set it equal to this idea and move this over, it's that. Here we go, you guys. This is a 5. This is a 5. This is the cube root of 125. This is a 5 squared. So it's 25 times 3, so it's 1 over 75 times this negative 5. This is 5. If you cancel that, that's a negative 1/15. This is 4 and 4/15. No. 4 and, I'm going to call it 4 and 14/15. Right? Is that okay with you?
Yeah.
That's my approximation for the cube root of 120. Now tell me what it is. What actually is it? I mean, give me a decimal.
4.932.
Okay, keep going.
424149.
2149. That's this number?
Yeah.
That's this number. Okay, thank you. What is the actual cube root of 120?
Oh wait, never mind.
No, that bottom number
The
is
bottom
the
number is the
actual.
actual.
Yeah, so if you're doing this work on a test, I ain't interested in, right, I want this number. Right.
That one's 4.9.
All right, so what's this number?
4.9 and a bunch of threes.
Oh, 4.9 and a bunch of 3s.
Yeah.
Cool. What's this number?
4.932424149.
All right, thank you. Hey, look at that. 4.9324, 4.933. Dude, it's awesome. I mean, this technique, I don't know, it's a pretty good approximation for the cube root of 120. If you're into stuff like that. I don't know, I like that question. I mean, this, I like this question. Which one do you want on the test?
Neither.
Neither?
Right.
I like the right one.
The right one.
You like this one?
Yes. Please.
Unless you give us the equation.
No, not that one.
Unless you give us like that.
Well, right, you have to figure it out. Right.
We don't really have time for that.
Well, you might be right. Time is always an issue. You're right. Yeah, I don't know. Maybe one of these will show up as a test. Maybe one of these will show up as a bonus question or something on the test. I don't know. We'll see.